All right, welcome back. Now we'll continue our topic in this internal flows. Now let's focus on the head loss. Okay, see head loss. That's the H sub L in the energy equation. And to give you an overview, recall that we have the Euler's equation before. Euler's equation, Euler's differential equation of motion for fluid flow. Then when we integrate this, we have the Bernoulli's equation. Except that in these equations, they don't consider the viscous effects, right? So no shear stress, even though we use the Newton's second law, F is equal to ma, right? So in their equations, there's no shear stress. And I've mentioned to you about the Navier-Stokes equation. And these equations, they actually considered the shear stresses, even though they applied the Newton's second law, summation of forces is equal to ma. However, the result of this, it's highly mathematical. And around 1900s, I mentioned also to you about the boundary layer by Ludwig Prandtl. That says that the viscous effects are only significant within the boundary layer. Okay, so that's the concept, and that's why because of this concept or this theory, it has simplified the Navier-Stokes equations. Okay, however, we have also another way to take into account the head loss or the shear stresses. It is by the use of conservation of energy, right? Together with the conservation of mass. So when we apply the conservation of energy, we can actually solve for the head loss, right? Now, if we rewrite the equations, we have this fluid energy, z sub 1 plus the velocity head 2g, right? Plus, or we'll just write the change, okay? The plus, if we have energy added into the system by a pump, or energy removed, h sub r, and then minus h sub l is equal to 0. Now, what is this h sub l? What is this? Okay, so there are many individuals who have proposed equations or descriptions regarding this head loss, and one of which is called the Darcy-Weisbach equation. Darcy-Weisbach equations. So again, this Darcy-Weisbach equation is just one of the many proposals regarding the computations of these head loss. Okay, so the equation of this equation is mathematically expressed as h sub l is equal to f times l o over d times the v squared o over 2g. Okay, this is the head loss. Right, this is our head loss, and that's the units would be in meters, because this is a dimensionless parameter. This one, L over D, that's the unit of length divided by the unit of length, and that's equal to 1. And this one is the unit of head. So our units would be in terms of meters. Okay, and by the way, some other text uses the symbol h sub f rather than h sub l, so that doesn't matter because it's just about symbols. Now, what is this F? This F is called the friction factor. Okay, this is called the friction factor, and more precisely, it's called the Darcy friction factor. Okay, so why it has to be emphasized that this friction factor is the Darcy friction factor? Simply because there are still many other friction factors that also use the word F. Like for example, the defining factor, okay, and probably many others. Okay, so if we use this, just note that this F is the Darcy friction factor. Okay, so this L is the length. Okay, that's the length of the pipe, right? That's the length of the pipe. Now, if you have a longer length, then of course you'll have higher head loss. Now, this one, the D is the diameter of the pipe. And that means if you have a larger D, then that means that's inversely proportional to the head loss. So the smaller your pipe is, then that's more hard to push the fluid. Okay, and this term right here, this is called the velocity head, and therefore this Darcy-Weisbach equation relates the friction, the geometry, this L over D. I say that's the geometry, and the velocity. Okay, velocity head. Okay, now the question is, this one can be known because we have encountered this already, the velocity head. The length of pipe is also usually given. The diameter of pipe is usually given, or it's the one to be solved, but anyway, it's just easy. But this Darcy friction factor, this F, where can we find this? Okay, so how to find F? Right, that's the big questions. How do we find F? So the first method, we can actually obtain that through equations. By using equations, we can solve for the value of the F. And when using equations, we have to determine if our flow is laminar or turbulent. Okay, so if it's laminar, the equation is F is equal to 64 over RE. Okay, so the friction factor is just dependent on the Reynolds number. So that's 64 over RE. But if it's a turbulent flow, then our F is actually, this is not equal. This is 1 over square root of F is equal to negative 1.8 log of these parameters, E over D, epsilon over D, raised to 1.11 all over 3.7 plus 6.9 all over RE. Okay, so this is actually an empirical equations and known as the Colebrook equations, or modified Colebrook equation. Another individual who had contributed to the development of fluid mechanics. So that's the Colebrook, modified Colebrook equation. Okay, so just take note that when you use these equations, this is 1 over square root of F. So you have to extract this F from the square root sign after you've done the computations on the right hand side. Okay, and this E, this epsilon, this is what we call as the roughness, surface roughness, and D is the diameter. Now the question is, where do we find the surface roughness? That can be found from tables. The tables in textbooks or in our lecture handouts have also attached the values for the surface roughness. In our reference text by Mott and Turner, we have this table 8.2, pipe roughness design values. So for example, if our material is glass, then the roughness says here that it's smooth, and we have a units in meter or in feet. Okay, so if our conduit is plastics, then this is our roughness, surface roughness. If we have a GI pipe, then this is our roughness. Okay, so the point here is this surface roughness can be found in tables. Okay, so that's the reason why that's the reason why earlier we introduced the concept of Reynolds number, simply because if we need to find the friction, then we need to determine if the flow is laminar or turbulent. Okay, now another method is by the use of the Moody chart. So this one is more graphical. An example of Moody chart is this one. Okay, so that's our Moody chart. In this chart, in the x-axis, you will notice there's the Reynolds number. So you have to define the Reynolds number in order to obtain the friction factor. So this is the value of F. Now on the right hand side, the right hand vertical axis, we have the relative roughness, and that's the ratio of the diameter to the surface roughness. Now depending upon the chart, this is sometimes given in terms of the epsilon divided by the diameter, or in this case this is given in terms of the diameter divided by the epsilon. So it's it's the reciprocal values. Okay, so just take note of this. If this is D all over epsilon or epsilon all over D. Okay, so this epsilon all over D, they're actually the lines right here. Right, they're actually the lines. For example, 300, if the relative roughness is 300, then this is the lines. This is the line. Now, in order to obtain the friction factor, you have to first determine your Reynolds number. Okay, so if you have your Reynolds number, let's say this is the value of your Reynolds number, and then this is your value of your relative roughness, then you have to find the intersection, and at that intersection, then you have to project it to the left, and then you'll obtain your friction factor. Okay, and another thing is that this is in terms of a log-log scale, so it's not really equally divided. In terms of the typical divisions of the graph, this is a logarithmic scale. Okay, and we'll also have here if the flow is laminar, and here we have a turbulent flows, something like that right here. All right, now I guess that's enough for now, and we will do some computations regarding what we have covered so far. Okay, so for our first computation, we have this problem. Actually, our first two computations would be about okay, 8.2, 8.3, determine would be about the computation of the Reynolds number. Okay, so for our problem number 1, okay, so for our problem number 1, it says here, determine whether the flow is laminar or turbulent if glycerine at 25 degrees C flows in a circular passage within a fabricated chemical processing device. The diameter of the passage is 150 mm. The average velocity of flow is 3.0 6 meters per second. We have data already here that's given. For a glycerine at 25 degrees C, the density is 1,258 kg per meter cube, and then the viscosity is 9.6 times 10 to the negative, I think that's negative 1. The 9.6 times negative 1 pascals seconds. Okay, so for the solution, if we write the RE, the equation for RE is just simply the velocity times the density times the characteristic length, which is just simply the diameter divided by the viscosity. Okay, so the velocity, it says here that we have a 3.6 meters per second, and the density is 1,258 kilogram per meter cube times the characteristic length, which is the diameter, 150 mm, and we have to convert this into meters. So that's 0.15 meters divided by the dynamic viscosity of 9.6 times 10 to the negative 1. That's Pascal seconds, which is just simply Newton meter squared times seconds. And this one should be comma. That's 1,258. Okay, so if you do the computations, what you'll get is a value of 708. Okay, so the units would be, okay, let's check the units. This one is kilogram meters per second squared. Okay, so if we simplify the units, we have meter cube, and then we have meters, then that's going to be meter squared, right? Or also this, that cancels out. That's meter, right? Meter, and then this one's meter squared. And here we have S squared, that's S, and we have kg. Okay, so that cancels out. Okay, so the value that we obtained is 708. Now we have to compare this to the critical Reynolds number. Okay, so since RE, this computed value is less than 2000, okay, therefore the flow is laminar. Okay, next problem 8.2. And by the way, this problem 8.1 is taken from the textbook of Mountain and Terror. That's example problem 8.1. Okay, so for our next problem, determine whether the flow is laminar or turbulent if water at 70 degrees C flows in a hydraulic copper tube with a 32 mm OD times by 2.0 mm wall. Okay, what it means that we have a OD stands for the outside diameter. Okay, so the outside diameter is 32 mm, but the inside diameter would be outside diameter minus the wall thickness. So the wall thickness, that's 2 mm right here, and another wall thickness right here of 2 mm, and therefore our inside diameter is equal to 32 mm minus 4 mm, which is just 28 mm, right? So 28 mm. Okay, so let's have here solving for the inside diameter. Okay, so the question is, why do we need to solve for the inside diameter? Simply because this is actually the actual geometry of the flow, the inside one. Okay, but sometimes if it's not given, then we just have to assume, or we have just to take the nominal diameter or the specified diameter. Okay, but if you want to be precise, then That should be the inside diameter. Okay, and says here the flow rate is 285 liters per minute. So we have Q, we have the big letter Q, the flow rate, and we have the diameter, which can be translated to area, and therefore we can find the velocity. Okay, so convert the flow rate to meter cube per seconds. So we have Q is equal to 285 liters per minute. Okay, so times 1000 liters per 1 cubic meter times 1 minute is equal to 60 seconds. And that's equal to 285 divided by 1000 divided by 60, and that's 4.75 times 10 to the negative 3 meter cube per seconds. Okay, so we have the flow rate and we have the area, then compute for velocity. Okay, so V is equal to Q all over A. So Q, 4.75 times 10 to the negative 3 divided by the area, which is just pi, times the 0.028 squared all over 4. And that's divided by, shift by, times 0.028 squared all over 4, and that's 7.71 meters per second. Okay, so we have now the velocity, and therefore we can compute for the Reynolds number. Okay, so RE is equal to the velocity times the density times the characteristic length divided by the viscosity. Okay, so our viscosity is given in terms of this dynamic viscosity, but the equation is dynamic viscosity, but what's given to us is the kinematic viscosity. And recall that this kinematic viscosity is just simply the dynamic viscosity all over the density, right? So therefore we can rewrite it as the velocity times the characteristic length divided by the kinematic viscosity. Now our velocity right here is 7.71, that's meters per second, and our characteristic length is just simply the diameter itself, and that should be in meters, 0.028 meters. Right, this is meters per second, this is meters, and then our kinematic viscosity is 4, okay, that's 4.11 times 10 to the negative 7 meters squared second. Now if you check the units, we have meters per second times meter, that's just meters squared. Okay, so that cancels out. And therefore our Reynolds number is times 1028 divided by 4.11 10 to the negative 7. Which is just 5.25 times 10 to the 5 times 10 to the 5. Okay, so since RE is greater than 4,000, therefore flow is turbulent. Okay, so if we do a recap on what we did, we are actually given, we're not actually given directly that we can just substitute it directly to the Reynolds number equation. So we have to find our way For example, we first solve the inside diameter because that's the actual diameter, and we convert the flow rate to given flow rate. So we have Q in cubic meter per second, and since we have the flow rate and we have the diameter, then we can compute for the velocity. Now that we have the velocity, but we're given the kinematic viscosity instead of mu, then we have to substitute, or we have to apply the relationship between this and the kinematic viscosity, which is just simply divided by the density. Okay, so once we have that, then we can just solve for the Reynolds number and compare the computed Reynolds number to the critical Reynolds number, which is 4,000. I mean, since our Reynolds number is greater than 4,000, then the flow is turbulent. Okay, now in our next problem, it says here determine the head loss if glycerine at 25 degrees flows 30 meters through a standard DIN 150 mm DN. That's a standard specifications, or one of the standard specifications for pipe. That's the DN 150 mm schedule 80 pipe with an average velocity of 4.0 meters per second. Okay, so I guess this is about head loss, and I think we'll do this problem in the next video.